Hey boys and girls, welcome again to Munro Live. And I'm here today with Michael Liedtke, an old guy I know from a long time ago. And he's brought along Tom Pilette, and you already know Tom and I. So we're going to talk a little bit today about batteries, a new style battery, a new chemistry for battery. But before we do that, I'd like to have Tom and Michael kind of give us a little background on who they are, where they came from, that kind of stuff. So who wants to start?
Go ahead, Michael.
So I'm going to start. My name is Michael Liedtke, and as Sandy was already mentioning, we go back quite some time. This is also the time, when I started my career in aerospace. So I was working for McDonnell Douglas and Boeing, and this is where I met Sandy many years ago. And there's a great thing. It's called CES, a trade show. This is where we met again just recently. But after I left aerospace and I went into automotive, worked for Mercedes-Benz, but then also BMW. And many years ago, one of my clients, he asked me, "Do you want to change the world?" And I said, "Well, what do you mean by changing the world?" "Yes, it's called energy storage, ultracapacitors." So I joined Maxwell Technologies, and I was the VP of Business Development for them for many, many years. And after I left them, I stayed in the energy storage industry. And then about 3.5 years ago, I joined Zeta Energy, a lithium sulfur battery company. We're going to talk about that a little bit later. And let me just pass on to Tom.
I'm Tom Pilette. Sandy, thanks for having us here today.
Yeah.
I've been in automotive my entire career, starting in the middle 80s, so more than 30 years. I was with Magna International for more than 20 years of that career. I left in 2017 to get into energy storage. I've been with Zeta Energy since 2017, working on the development and commercialization of our new lithium sulfur technology. We think it's going to be instrumental both from a cost perspective and a material availability of really driving the next generation of energy storage, both in automotive and beyond. And we're happy to be here.
Well, I'm happy to have you here. Tom, did you want to maybe why don't you give us a little background as well, so
sure.
We'll know who...
So I'm Tom Prucha. I'm Director of Electrification for Munro and Associates, and a long history in vehicle electrification, basically anything high voltage, and now with a great focus on batteries and their cells and the chemistries within. So fairly well studied on the subject and very interested in understanding this new, what I would call, from the looks of it, a breakthrough technology that is coming quite nicely.
Yeah, it looks very good to me. So what I'd like to do first is, I guess through dumpster diving or something, you managed to get a couple of these caps. And I was wondering if you could maybe talk us through a little bit about what looks to me to be like tabless technology. And also, as everyone probably knows, Tesla bought Maxwell and dissolved it, I guess, yeah?
Right, that's as far as I know. And as Sandy mentioned, sometimes you got to know which dumpster you have to dive in and what you have to pick up. And so what I found here, were some old tabless design cells for ultracapacitor. And it's actually something that's very common, in the ultracapacitor industry. And the thing is, that this was already conceived, back in the late 2000s. And what you see here, is like the active area from here to there. You see the tabs here and here. And then you see the famous, infamous current collector up here. And you see it down here as well. And so through this current collector, we avoided the tab, using any tab. Because this current collector basically connects to all, the individual slivers, of current collector coming out of the jelly roll. In this way, it was done, and everybody's doing it this way, to really reduce the internal resistance of the ultracapacitor cell. So an ultracapacitor is, for those that might not know it, it is an energy storage device that is very, very high power. This is why everybody is very keen on reducing the resistance, but they carry very little energy or limited amount of energy, which is then defining somewhat the market for these products. It is, you still find them in tens of thousands of wind turbines as a power backup system for the pitch blades. You find them in a lot of stop-start system. Stellantis is actually still using that for their stop-start system. You find them in many grid application. You find them, also in hybrid buses in China. This is where really the market took off. And this design here, that you really introduce, this kind of this disc on top that collects all the currents and allows you to quickly bring it to the outside of the can. This is pretty much the core technology that a lot of other ultracapacitor companies are utilizing as well. So I have to say it was very interesting for me, or kind of brought back good memories, when I heard Elon Musk the first time saying, oh, we're going tabless. We didn't know back then that this is called tabless. For us it was always the natural thing. But it's interesting to see that this is now getting somewhat of a revival. And a lot of companies are working on that and trying to figure out, how can they optimize this process? Is there still room for optimization? Yeah, but we're not going to talk about that.
No, we're going to talk about your process. But I thought our audience might be kind of interested in finding out what did happen to Maxwell. And now you know a little bit anyways. But what I'm really interested in is, actually Tom and I are very interested in, is your process now for coming up with these new sulfur batteries. And I really, we're probably not going to say a whole lot. We'll probably ask questions, but right. I'm definitely interested in hearing a little bit about what you've been working on.
So now we're going to switch things a little bit. We go over to the latest company I'm working with and I'm proud to work for is Zeta Energy. So it's a startup. We're based in Houston, Texas. And this startup, has been up and running already for about 7-8 years now. But we just finished our Series A was February last year. And since then, we moved into our own new laboratory. We got everything there now on site that allows us to really further this development of the cell. We're building our first 1 amp hour pouch cells. We're going into larger cells, this year. And I think the key thing about this technology is, how is this battery, put together and what is inside. So I think the one thing that is very unique, you see a lot of companies out there, that develop a component of the battery. Either this or that, the anode, the cathode material, maybe they develop a new separator, they develop this, they develop that. But I think for us, is we developed the entire battery system. Yeah? So we developed our own cathode and we developed our own anode. And with that, we developed the materials for that, which is also very unusual. And it is what we refer to as a lithium anode with a little caveat. And we're going to get into that one a little bit later. In between the cathode and anode, was always for us, one of the prerequisites. We wanted to use industry standard materials. So the electrolyte is using a standard solvent, and we mix it with a lithium carrying salt, just like everybody else. We put this in between. And now separating the whole thing is a separator. And right now we're using a separator from Toray. So this is a separator, this is a standard off-the-shelf separator, and we're also going to be looking into separators that will be built here in the US, or if we have a facility in Europe, in European-built separators. So basically, none of the materials, always the theme is, do not use unobtainium. Don't use anything that you cannot get. It always has to be something that we find openly in the market, and we can have also then a nice competition going on. The technology, and this is what we laid out here in our roadmap, we're shooting for a 450 watt-hour per kilogram technology. In the past, a lot of people were saying, lithium sulfur, it might not get that high on the volumetric energy density, but we will also be able to compete on the volumetric energy density. And together with these two components, the energy density, and then also, the C rates, we will be able to get to very high C rates, makes it a kind of a high performance battery technology. But then there always comes the question, well, what about the cost? And this is the beauty. What we're doing is we're using very low cost materials. So now going into the cathode, we already shared that, with Sandy and the team, but here we're using sulfur which is basically a byproduct of every refinery out there. And we checked, I think in the US, there's like 100 and something refineries. If we take the Canadian refineries in there as well in there, we're getting close to 140, 150 refineries, you know, that are in North America by itself. Every one of them is producing sulfur, and everyone could be providing us with a sulfur. And so the sulfur, you know, we already built our first cells using refinery sulfur, not something that we bought, you know, at some chemical or chemistry specialty store, you know, where you get the purified sulfur. No, we used the sulfur from a refinery, ground it up, put it into our raw material. We mix that with a polymer, and then the polymer is also something that's widely used. Maybe, Tom, you want to say a few words about the polymer we're using?
Widely available. It's the backbone for carbon fiber. Definitely a material that's available everywhere. So it's not an issue for us to procure it. Michael mentioned early on, unobtainium. Not only do we not want unobtainium, we want to have low-cost raw materials for our input, for both our anode and our cathode, and that's exactly what we've done in the development of this battery, making sure that those materials are not only low-cost, but available, and available where we're going to manufacture these batteries.
So the last but not least, you know, we're using conductive carbon. In this case, we're using carbon nanotubes, and we bring these three components together. You already notice here, no metals. No manganese, no nickel, no cobalt. None of that stuff is in there. So basically all these materials, you know, you can, you know, purchase it right here and produce it locally here in North America or in Europe or wherever you want to set up your plant. We take these materials, we blend them, and then we create, you know, what we call like these granules, and I always refer to them as a, it would be something, well, a Nescafe material. But it would be the espresso version of Nescafe. And we do this, you know, for various reasons, but the number one, in the processing, we don't want to have that much of a dust generation. So we take this powder, or these granules, introduce them into a pyrolysis reactor, and the next thing we get out of them is this kind of little nice black material. And this black material is what we refer to as our sulfurized carbon. This is the main ingredient, you know, on our cathode material. We take that and we then add water, so we don't need to use any nasty solvents. Just add water, create your slurry, and coat it onto the aluminum foil. But we're also working, as even though we're a startup, in parallel, we're already working on how can we scale that up. And this is what it would look like if you scale it up all the way to a big rotary kiln type reactor, where you enter the material on one side and let it run through the to this kiln, to this rotary kiln. It will take some time, but then at the end of this process, you know, you will have the finished material drop out, and you can go do this like on tons per day level if you want to.
This would be a similar process that you utilize in LFP material development today, identical in the rotary reactor.
Right. So we already built together with a partner. You know, we're utilizing their piece of equipment. And this is one of the mottos of the company. Try to see what other people are doing in other industries and see if this is applicable to what your needs are. So this company here, they're known to do food processing, pharmaceutical, cosmetics, and we're doing this process there right in their house to create the sulfurized carbon on a kilo level per day range. Yeah? And the next step for us would be then going into the rotary kiln. So this is what is needed, you know, to produce the cathode material. So now it's getting even interesting because now we're getting into the anode. And we said, you know, we're a lithium metal anode with a little caveat. We're using carbon nanotubes to support the lithium. And so how we're doing that one, some people are asking, well, are you guys buying carbon nanotubes? No, we're not buying carbon nanotubes. What we're doing is we're using standard copper foil that we just buy off the shelf, and we introduce this foil into a physical vapor deposition piece of equipment, the same kind of equipment that you use to coat chip bags, you know, with a silver lining in there. You use it to coat reflectors in automotive. I mean, there's millions of applications where this is being already used and the equipment is readily available. Again, the same philosophy, use somebody else's pieces of equipment. So now we put the catalyst on there. It's only nanometers thick, and then we expose this in a chemical vapor deposition piece of equipment to hydrocarbons. And these hydrocarbons, they are the source of the carbon to then allow us to grow these carbon nanotubes. So we get these vertically aligned carbon nanotubes, and as the next step, we lithiate these carbon nanotubes, what you see here. I hope you can see that right here. And in the microscope, you can even see, how bundles of these carbon nanotubes are coated with the lithium. Now here we have a nice little image of what the reactor, this is like a prototype reactor that was built with a partner. They built it with us or for us. We're introducing the copper foil that has been coated with a catalyst in this reactor. And now here it gets beautiful, and this is where we get there. These are the carbon nanotubes. These are some of our, after like a couple of weeks worth of work on this equipment, we were able to get these carbon nanotubes. This was on a single side. And what you see here, at the bottom is the copper foil, and then the little whitish line, this is the catalyst. And now this was only on one side. We also done it already double-sided. Here you see the see the copper foil here in the middle, and the carbon nanotubes grown on top and bottom. In this case, it was up to 75 micrometer height. Some of you might wonder, what is this here on the side here? And this was when they were preparing the sample, some of it actually accidentally ripped off. But the case in point for us was to demonstrate we can grow it on both sides of the copper foil consistently at the same height on this copper foil that was introduced.
And maybe as important, in a process like this, when we were working at the chip level, growing nanotubes would have taken a very long time. Today, we are processing this material very quickly, 30 seconds to full growth, and we can do this in a roll-to-roll piece of equipment.
And full growth, you were talking about 170 nanometers?
Yeah, we don't necessarily need that high. What we're doing, Sandy, is optimization so that we can reduce the overall time and increase the throughput of that electrode. So yes, we're doing it, but what that does is it really shows the real efficiency of this material to grow and to grow quickly and to do it repeatedly. And so this is the processing work we're doing today.
All right, so we've looked at this, and I guess a lot of the stuff is leaving me in the dust. First off, I know a little bit about growing nanotubes, or at least making them the way you are, out of basically sewer gas. It works really well. We made flat diamond technology work about 20 years ago, and that's basically how you have really, really fast circuit boards, is by using flat diamonds. This has gone like 2 or 3 steps beyond that.
It has.
And it looks like you're going to be able to do everything internally, correct?
Correct.
Right.
Yes.
Yeah.
That's exactly right. And that really does highlight the low cost of the processing of these raw materials in both our anode and our cathode, keeping the overall cost at the cell level well below $50 per kilowatt hour at gigacapacity scale. And so we believe that it's going to be not only a very efficient battery, but it's going to be a low cost and readily available battery. And that's going to be real important if we're going to really achieve the growth in electric vehicles in the very near future.
Well, I like the fact that there's no metals inside of it. I see nothing with oxide in it, so it means there's no oxygen. If there's no metal and there's no oxygen, chances of it catching on fire is like slim or zero. And I like that part too. So let me ask you a question. Who else is doing this? Anybody else?
Yeah, there are a lot of people that are attempting to do what we've already done. And really, when you think about what's been the Achilles heel of the lithium sulfur or sulfur batteries in the past, it was the polysulfide shuttle effect. And what Zeta has done is, instead of trying to pacify it or to try to mitigate or reduce a polysulfide, we have a process that completely eliminates it. And polysulfides have been the limiting factor in cycle life and the deterioration of the anode in lithium sulfur batteries in the past. If you start with a technology like we have, we really change the state of sulfur. When we talk about sulfurized carbon, we really are realigning the carbon chain of sulfur and allowing it to provide the energy structure that we need on the cathode without giving up the performance of what is a hindrance in elemental sulfur today, which is the creation of a polysulfide shuttle effect. We don't have that. And so we think we're starting from a very good position in order to make a very low-cost technology perform and cycle, very high cycle life.
Well,
So let me just add something to that. You know, we had in the beginning a few skeptics. You know, they were saying, "Oh, you know, too many people have already said, you know, we solved the problem and this and that." You know, we're really skeptical about that. And one of our partners, and actually ultimately two of our partners, you know, what they did, you know, they built up some cells and they started cycling them. And the very first dead giveaway was, you know, after they were done 100+ cycles, they took the cells, opened them up, and the separator was snow white. There was no yellow in the separator. And that was for them, instantly the dead giveaway. There is no issue with the polysulfide. There is no sulfur being dissolved in the electrolyte.
We've had that third-party validated.
Right, and we got this, you know, here in the US and in Europe, you know, 2 independent third parties verified, you know, that we solved the problem. And interestingly enough, you know, both of them, they were skeptics of the technology and they say, I don't know if we want to work with you guys. And once they opened the cell and saw that, they said, okay, we're going to work with you guys.
Well, the other thing is dendrites. Now, I wanted to maybe just go on that a little bit because that is ultimately the killer associated with most batteries. So you guys have said that you're not experiencing growth.
Yeah, so the anode, where you experience a lot of the dendritic formation, we have a unique protection methodology in the SEI layer. So when we plate lithium on the carbon nanotubes, that forms a very robust SEI. And so what we do is we protect through that hosted lithium and really prevent the formation of dendrites. They're really locked out. They cannot begin to form. And that gives us a safety factor, even at very high power, even at very high charge rate.
Well, that's the other thing that just dawned on me. Maybe some of the folks in the audience don't know what a dendrite is. So seeing as you've been quietly waiting for your turn. Tom's usually pretty vocal. But anyway, why don't you give us a description on dendrites and...
Sure. So dendrites form under various circumstances, particularly when charging when cold. I understand that's one of the bigger problems to solve, so I'll be curious to hear how you handle that. But yeah, they form what amounts to a short circuit that can be the end of the life of the cell. It certainly degrades its capacity as a early indicator, and then eventually it's what kind of takes the cell out of commission. If it doesn't cause an event through a dead short circuit, that is the kind of event nobody wants.
I call them actually little Christmas trees. Yeah? So when they start growing, they look like little Christmas trees, and then once they grow big enough, they poke through the separator, and they will work their way through the separator. And there are some people even claiming, even if you have a solid electrolyte, they might find their way through there. And then once they find their way through there, you got the micro short, and then it's just a question of time.
Yeah, and of course, with the solid electrolyte, there's a hope there that it's solid enough where it keeps them from growing through. But then, to your point, yeah, they're pretty pesky little things, and they can find their way through. So
I'm losing faith in the in solid state. I keep hearing it's just around the corner and stuff like that, and I don't know. A friend of mine, Don Runkle, said that it's like trying to glue potato chips together, and I haven't quite figured out how to do that yet. So maybe it's a little tougher than everybody thinks. And everybody that I've seen so far that has said, "Oh, come and look at my solid state battery," it turns out that it's not a solid state, it's a semi-solid state. In other words, there are, well, actually, Tesla's dry cell looks pretty damn dry to me, but it's still not solid state from what I can gather. And other solid state companies that I've gone to look at, they're saying it's solid state, but it looks kind of moist to me. So maybe it's a moist state. I don't know.
Really, the key isn't so much whether it's a solid or a liquid; it's that it's not flammable as a solid state.
And that's what I like. I like the fact that I could make. Maybe we should touch on this as well. I was going to say, I'm looking at cylindrical. Can you make this a cylindrical battery?
We can. We're form factor agnostic because we have traditional coated materials or grown dry materials on our anode. We can take any shape there is. We can be in a cylindrical jelly roll. We can be in a prismatic. a pouch cell, any of that form factor works fine for us. We say that the technology is available today utilizing a safe liquid electrolyte. And when I say a safe liquid electrolyte, the prevention of dendritic formation or microshorting, we mitigate the technology or mitigate those concerns with the technology. And so today's technology is using a liquid electrolyte, but we're also future-proof. We've done early benchmarking and studies that our materials work in solid-state material formats as well. And so we don't have to wait until some of the critical developments continue to occur in solid state. There's a lot of things that we've all heard about solid state. When's it coming? When's it going to be available? What are the limitations? Do we have to preheat the battery? Does the battery have to be under constant pressure? Ionic transport isn't easy. A liquid electrolyte makes it much simpler. And if you have a safe condition in the battery, it should be a safe operating condition inside of the battery system. And so that's what we're doing. We're trying to develop the safest liquid electrolyte and being available for solid state when it eventually gets here.
Yeah, translating the liquid electrolyte is usually highly flammable, and it's usually the main reason that the cells light on fire. And then, of course, with solid state, the hope is that since the electrolyte is not flammable, then the lithium metal anode, which is new, most people don't realize there's not much, if any, lithium metal in a lithium-ion battery today. But there will be when we have solid-state electrolytes.
Right.
And then the concern is, with lithium metal being present, can that cause another problem that the electrolyte didn't solve, and that is the lithium metal fire. So I'll be curious to see how your lithium plating technology on the anode mitigates risk against that and allows you to use this conventional electrolyte and not have to go to the solid state to make it work.
Yeah, so, therein is where we're headed right now in doing all the safety validation, extensive safety validation. The one thing that we pride ourselves on is making sure that we're doing the work, we're promoting the work, and we're letting the performance of the battery speak for itself. You mentioned the safety aspects, whether it's a liquid or a solid electrolyte. You're absolutely correct. And one of the things that we have to do is look at all the input materials, both on the anode and the cathode, eliminating the metal oxides. That's a good thing, no oxygen in the battery. Stabilizing the SEI, making sure that it's as robust as possible. Already using a three-dimensional lithium metal gives us a safety factor, making sure that we have dendrite suppression, that it does not propagate, and so that we protect that battery the best we possibly can in the conditions within a liquid electrolyte, and that's what Zeta does.
Well, here's something that I'd like to add as a suggestion. I'm a big fan of cylindrical. I am not as big a fan of anything that's pouch or prismatic, and the reason for that is because it's so easy to damage those pouches, and once they're damaged, I'm not going to catch something that size on fire. I'm going to catch something this size on fire that I can't possibly put out. It's just not going to happen. These cylindrical batteries, if one does get unhappy, okay, I lost a cell. And I've lost, what, 3 volts and I don't know how many amps, but let's say just for now talking 3 volts. If I burn off the 2 leads to the anode and cathode, okay, now I mean, can my battery survive? Yeah. Actually, lots and lots and lots of cylindrical battery packs have had situations where
cell drop off.
They got cell drop off, and actually it doesn't do anything. The efficiency or inefficiency doesn't make any bit of difference. But when I got a pack this size and I lose something inside there, I've lost that block because I can't balance it anymore. It's like, so I would like to suggest that if you decide to get into the battery business, just stick with cylindrical, and then we'll recommend them. We'll recommend you to their customers because
it is an added measure of protection.
Right. I mean, it's a nice casing around that, that's a lot thicker, than just the pouch cell material.
Yeah.
I always like the fact, that you can assemble them so much faster. You just put them on a winder and like within seconds, you have your jelly roll. So all these process steps are very, very solid. They have been, tried and tested, with with traditional capacitors, electrolytic capacitors. They were also using the same process. This is a very mature technology. The thing that's maybe new to some of these cells is, that you want to do this in giga scale capacity. And that's where you then have to introduce, some different type of machinery. But again, it's not rocket science, it can be done. And, I've done it, during my Maxwell days, skeleton technologies, shout out to my friends in Estonia. They've been doing it as well. Yeah. And, it really works. And it's very, to your point, there was one time a requirement that we received, from an automotive customer. Yeah, you have to pass the drop test. And I said, well, what's the drop test? Oh, you take the cell and you drop it from 1 meter. Well, 3 feet. Okay, here, I just drop it and, well, you need to prove nothing happens. I said, well, it's pointless. You can drop this thing. Nothing's going to happen.
Hit it with a baseball bat.
Right.
Yeah, as far as speed, prior to getting into the auto industry, I was in the machine tool world. And the company that I worked with, Valiant Machine Tool, we decided, or we were given the opportunity to work on canning equipment. And I know how fast you can make a pouch battery, but I know it's much, much faster to go to cylindrical because I watched cans going down to the point where it's just a blur. And they were getting filled up with corn and lids. They never touched anything.
Right.
They were thrown like frisbees with a little, like a magnetic ring, and throwing them down, and they just basically coasted on the air until they fell into the. This is the way to do it, as far as I'm concerned. If I want to get down to a lower cost with a higher sense of safety, I can't think of any other reason for doing anything but cylindrical. And then, quite frankly, the biggest electric car company on the planet, they use cylindrical, and they seem to be pretty happy.
Sandy, I like cylindricals myself for maybe some different reasons. I'm kind of a performance enthusiast, and you'll notice that the Tesla Plaid are king of the hill until the Sapphire comes along. Yeah, it uses cylindrical cells, and the very smallest ones. There's a number of reasons. But one of the things that always comes to mind is, especially in contrast to the pouch cells, is the expansion that occurs.
Right.
Yeah. And it's on the anode side where it's collecting lithium ions. It grows quite large, and depending on how much silicon content there might be in there, it could be extraordinarily large, and it causes the pouch to swell a lot. Mm-hmm. There's a lot of pack design effort that goes into managing that swell. Mm-hmm. So I'm curious, it could be, while you have your preference for cylindricals for one reason against the pouch, one of the things that I don't like about the pouch is that expansion and how you have to manage that so extraordinarily. So can you speak to the expansion of your anode?
Yeah, we can. We have very little expansion, and that's due to the materials. And that's another reason it's a much safer battery. We don't gas, so we're not a company or a material that needs a degassing stage, and we don't see the swelling that you see both in graphite and in silicon anodes. We have very little expansion. And if you think about the surface area of our anode, and you think about that density of that carbon nanotube forest, right? Mm-hmm. You think about the room that we have in there. We already have it built in, and so we're not expanding.
So one of the things you don't like about the pouches, they're so easy to break. One of the things that makes them break is the expansion.
Exactly.
So they may have a technology that's similarly suitable for pouches, and it could breathe new life into the pouch industry.
It could be, but it seems like to me, Tesla was the first one to announce it, that they're going to go sell, cylindrical wise. Others have jumped on board as well. And there's one company, they told me, never in a million years are you going to see cylindrical cells in our cars. They just announced a few weeks ago they're going to have that. So, there's others jumping. And maybe to your point, maybe there's something that comes out, that, will, make the pouch cell safer. Or
we may see legislation that drives that safety, that increased safety form factor requirement. We may not. And, today, we're very fortunate in the development of both the BMS systems and some of the software technology, the algorithm control, that we can anticipate some of the bad things that are happening, side reactions, voltage anomalies, some of the concerns with heat, and even expansion. And so if we have a smarter battery, we have a safer battery, we can mitigate a lot of it. In the meantime, as I said in the beginning, we're form factor agnostic. We can be in any form design that's out there.
At the end, we say, it's the customer driving it.
It is.
If the customer says they want to have triangular shape, we'll see if we can make make it work in triangular.
Yeah.
So,
Well, you mentioned your power performance is enhanced as well, so high C rates are coming.
right. So we've tested already up to 10C, and 10C this is significantly high and sufficiently high. We were just chosen to participate in a program by ARPA-E,
Department of Energy.
the Department of Energy. And one of the prerequisites that they had, for this new program, EV for All, that they want to introduce a technology that allows people that don't have a garage, that don't have time and space, or maybe also the money to park their car somewhere where it's being charged overnight, that they can then later on drive the car, go to a charge station, and just maybe recharge in 10 minutes to get to another 80% of the charge of the vehicle and keep going. That they just say, to really, for electric vehicles to really take off, you need to have the fast charging.
So let me get that right. When you say 10C, you're talking about a charge C rate.
Yeah.
Wow, that's impressive. I mean,
Not 0.1, not 0.2, 10C.
and not what might be fairly normal for some of the lithium-ion chemistries in discharge. You get that sort of C rate, but in charge, the DOE has this mandate of 6C to get us a 10-minute charge cycle,
Correct.
and you have to be able to do that at least 500 charge-discharge cycles and still retain 80% of your capacity.
Correct.
So can you speak to the capacity retention after cycling? Is that something you've done enough of to know anything about?
We have done it in small cell format. We're continually running it now in larger capacity cells. We'll have much more data by the mid of this year, and we'll share some of that information with you. But we've exceeded 1,000 cycles in our cell format to date. On half cells, we've gone 3,000 cycles. And so as we continue to refine and control, and when you get into larger format cells, the basic chemistry is the basic chemistry. What you have to do is you're managing tolerance and making sure that the precision and the build tolerance of those batteries remains consistent. And so as we do that, we're going to have higher and higher cycle life in our batteries as well. So even with a high charge rate, you're not sacrificing the cycle life in our battery technology.
There's another interesting phenomenon that we observed, developing this technology. And it has a really, really low self-discharge. So one of the inventors of the technology, he built a little pouch cell and he charged it and then he put it on the shelf. And it was sitting on the shelf for 5 months. And after 5 months, he took it off and it was less than 1% discharged. So that we predict, within 1 year, we'll probably come in like 3% discharge. So now if you think about that, it also allows us a completely different set of applications. I'm thinking about remote applications. If you have your battery sitting somewhere in the middle of nowhere.
On-demand power.
On demand, that you need it maybe very infrequently.
But you need it.
But you need it, It could be for all these, disaster situations, that you have a cell phone tower. This thing sits there. It just keeps sitting and sitting as a backup system, nobody takes care of.
Similarly to lithium primary batteries,
Exactly.
where you have a 10-year or more lifespan with it
I don't know
holding
if
its
we
energy.
want to go to 10 years yet, but...
Yeah, well, but the point is, people look at the lithium primary battery technology for that long term, and here you're able to achieve that with a rechargeable battery.
Yes.
So that's pretty extraordinary.
Right. So it would not necessarily be the deciding factor for automotive. Even though there are these airport parking requirements that you go on vacation and
parasitic
then
loss.
Whatever 5 weeks later your car still needs to run. But there's numerous other applications.
Wait a minute. Who could afford 5 weeks at an airport parking lot?
That's a fact.
That's even more expensive than your vacation.
That's almost a new car.
If these guys are listening that gave me this requirement, this was exactly my answer to them.
Yeah.
Are you serious? Who parks a car for 5 weeks in an airport? You can have a Rolls-Royce chauffeured vehicle pick you up, and drive you home.
Helicopter. You could have a helicopter come and get you.
It might be popular in New York where they have
things-
high parking fees. Maybe maybe it's cheaper at the airport.
I don't know. Anyway, the other thing that I was always thinking about was going back to the super caps. I was always wondering, I know if I have that and I want to discharge it, I'm going to get whatever power is inside, and I'm going to get, some people call these things lightning bolts in a can. But what happens if you made the cans really small and then you fired them off, in regiment, and then use that to charge your car? We were talking about 10C. My brain did not register. When you said 10C, I was thinking 10 cc's, 10 cups? What is he talking about? I had no idea that, or my brain wasn't ready for a 10x charge. That charge rate is like absolutely phenomenal. But I did think that, you know, I've seen, we use in military devices, sometimes we'll use little capacitors, supercapacitors that are really, really small. And they fit in, you know, something that I want to blow up. So what happens if we just had a whole blanket of those things,
I mean,
and you just fired them off, you know, a little at a time?
You still can, I mean, you still would definitely, you know, get the sequence, get a lot of power. The problem is always the supercapacitor, they don't carry enough energy.
Oh, no, I'm talking about taking the supercapacitors and charging my battery.
Okay. So
if I wanted a bomb to blow up, that's what I want. But if I want to if I was trying to take a capacitor to charge my battery, I can't do it. The battery just can't soak it up fast enough.
Right. So I mean, you have to limit it.
Enough energy either, really.
But the thing is also, you would have to have a relatively huge bank of capacitors.
Well, I'm thinking of the whole top of the battery pack. I'd fill them all up and then just fire them off, you know, at a rate that the batteries could.
The problem with, I mean, it's always been the holy grail, you know, that ultra capacitor thought, okay, now if we can somehow combine it, you know, with the battery,
correct,
we got the best of both worlds, you know, high power and high energy.
High quick power.
I've been studying this for a lot of years.
There's actually, interesting enough, there's a project here in town with GM, and they showcased a box. And it was a 12 volt and 48 volt system. In between, as they were switching between 12 and 48 volt, you know, they used ultra capacitors to buffer it. That was basically the first project that I've seen that was presented publicly, you know, that was utilizing ultra capacitor with lithium ion batteries.
Yeah.
And they were using it, you know. So unfortunately, I haven't seen the gentleman in a while. Hello, Dave. And he would tell me then, you know, how this thing is coming along. And but there are people that have been thinking about that.
We saw a couple of examples in racing, right, with the e-drives, where we saw a bank of ultra capacitors that were bolted on the front end of energy storage. And so if you start thinking about the demands of that type of a driving situation, you can see where that makes a lot of sense.
Yeah, we've used them on robot systems inside of warehouses and whatnot, supercapacitors.
They were perfect for that.
Yeah,
perfect.
Absolutely wonderful. Now I've got to,
it's the quick jolt.
I want to just, because we're going to run out of time, I want to shift gears a little bit, and I want to ask about LFP versus your process there. LFP, people are starting to talk about $70 per kilowatt hour. What do you think yours is going to come out at?
We'll be less than that for sure. We have line of sight that will be under $50 per kilowatt hour.
At the cell level.
At the cell level, yeah, not at the pack level, for sure at the cell level. And so, look, LFP it's a great alternative if you can afford the weight penalty. You're going to have that.
Yeah.
So if you're looking at it for a long-term automotive play, I don't know if it's necessarily the best thing. If you can find a lower cost technology that's lighter in the same space, I think you have a much better option if it's providing the same ultimate performance in that energy storage system. So we think we have that.
Yeah, that's the big elephant in the LFP room, is nobody wants to talk about how much less capacity it has.
That's right.
You need more mass of it.
You need more mass of it.
Same sort of energy density that you would have, or same energy content of NMC or any one of the other variants.
But you know, at the end of the day, Sandy, we look at it this way. There is not going to be a single technology in 5 or 10 years from now. No. There is going to be a wide range of different battery technologies. And the pie is really huge. Even a small slice out of that pie will make everybody happy, including us.
Yeah.
And so
Michael mentions the word startup. I think it's important. We started in 2014. We think we'll have an automotive grade battery ready by 2027, 2028. 27 is very earliest. And so it's a 12-year startup, and you hear the story a lot. It is a lot of development. It is a lot of safety protocol. It is a lot of refinement. Most importantly, it's the consistency of that battery chemistry and technology to make sure that you're meeting automotive specifications for a safe operating energy storage environment. And these are the things that we're focused on.
And you know what? That's a wonderful place for us to say goodbye. because I always like to end on a high note, and that sounds about as high as it's going to get with this crowd. So anyway, thanks very much for watching Munro Live, and thank you to Michael and Tom
Thank you.
And stay tuned. We're going to have some more. Actually, Michael and I are going to talk about
History.
how to kill a complete industry all by itself, all by yourself. So anyways, thanks again for watching. Bye now.